Hello everyone, this is chapter 7.3, which discusses basic counting principles. Now in fact there are only two that I'm going to go over here, so this is potentially a short video, but I guess we'll have to see how it goes. The first counting principle I want to talk about is the addition principle for counting, which basically discusses how to count the number of sets in the union of two sets. So this says that the number of elements in the union of two sets A and B is the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B. And the reason why this term is here, that we're subtracting, people often get confused of why this is, but I've written this already here in red. This is basically from double counting. So if you were to count the number of things in A and then the number of things in B, I guess you can kind of see with a Venn diagram. So just to show you, let's say this is our universal set, and we have, let's say, A and B. Well, I guess that's fine. I want to make it look kind of uniform. Still make it look bigger. All right, that looks a little better. So let's say this is A and this is B. And let's say you want to count the number of things in A or B. So remember how we shade. So let's consider shading kind of like counting. So when I shade a region, I'm counting that number basically. So here, if I'm counting the number of things in A, that's shading this basically. Now, if I then, because I want to shade the whole union, so I want to count the union of A and B. So if I then count, so I already counted A, but then if I count B, notice I'll be overlapping the intersection. So I'll be double counting essentially. So if we subtract the number of elements from adding the number of elements in the intersection from the addition of the number of elements in A and B, then we'll get legitimately the number of things in the union. So that's really just the explanation of why that's there. And then finally we'll get this picture. So there's like an intersection that's counted twice basically, but when you subtract it once, then you're not double counting anymore. So that's the idea there. Now for this example, this is obviously an application problem here, but let's read and let's see if we can try to figure out what things are. Now notice there are only three numbers here. So chances are one will be one of them, one will be the other, and one will be the subtraction term, but I'm kind of seeing a little too far ahead. Let's read and see what happens. So it says for business firms in a certain city, 750 offer health insurance, 640 offer dental insurance, and 280 offer both health and dental insurance. Okay, so there's some key words here. Of course, these are the three numbers I was talking about. And well, we have these two types of things. We have dental, we have health, and we have health and dental. So and reminds me of intersection, so this is the intersection of the two basically. And now finally they ask how many firms offer either health or dental. So either really isn't a keyword, but or is the keyword here. So or should remind you of of union. Now again, or in our definition of doing it is one or the other or both. So it is possible that it's not just, dental only and then insurance only and then health only, but it's health or insurance or both. So really what we want to do here is we want to call these sets different things. So I'm going to call H the, so let me call H the set of all firms that offer health. So let me just call it H, I guess. I'm going to call D the set of all firms that offer dental. And then, well, that's really it. So what I'm going to notice here is the number of H, the number of things in the set H is 750. And the number of things in the set D is, of course, 640. Now, I didn't write a labeling for health and dental, and that's, of course, because that is the intersection of H and D. So the number of things that are in H and D, so the number of things in the intersection, of course, is given to be 280. And now what are we asked to find? Well, this or means union, again, and we're asked to find the number of things in that union. And from the counting principle that we just kind of discussed, well, this is just the number of things in H plus the number of things in dental, D, minus the number of things in their intersection. So just replacing these things with those numbers, we get 750 plus 640 minus 280. So I'm getting that 75 plus 64 is 139. So these add to 139 with a 0 at the end. And then finally subtracting 28 with a 0 at the end. Well, notice 39 minus 28 is 11, so this is just 1,110 as it turns out. So the number of firms that offer either health or dental or both is this amount. All right, so now we're going to see this is the only example I wanted to do for the addition principle. I could do one that's more abstract and less applicable, but really what you would be doing is just literally counting things in A, counting things in B, counting things in their intersection, and then applying this. So I think it is more practical to see an application problem like this, even though we're just legitimately labeling things and playing with the formula anyways, but that's what I'm going to do. So now we're going to take a look at the next principle I want to talk about, which has to do with multiplication. So let's see that right now. All right, so here is the multiplication principle for counting. By the way, this is often known as the fundamental principle of counting, but the book here calls it the multiplication principle, which I think is fair because it has to do with multiplication. And here it says the number of ways of performing certain tasks is the product of the number of ways that each task can be performed. So as a quick little example, I say if T1 and T2 are tasks that are going to be performed, then the number of ways of performing both of these tasks, T1 and T2, is the product of the number of ways of performing T1 and the number of ways of performing T2. So I guess there's one kind of detail I'm missing here, and that is that you must perform T1 and T2 in that specific order, or else this principle fails. So let me just kind of say here that order matters. Order matters. And when I say order, I'm talking about order that in which each task is performed. Now this is kind of technical detail that I don't think we really need to worry about too much, but let's just go ahead and try to find the result for this example here, and let's see if we can see it creep up maybe. So here I ask, how many 3-letter codes are possible using letters A through H only if we are asked to do one of each of these three? So no letter can repeat, repeats are allowed, or adjacent letters are not the same. So in other words, no number next to each other will be the same, but repeats could be allowed. So for example, ACA is certainly a possibility for 3, but not for 1 because there's repeats. For 3 it is, of course, because A and C are not the same and A and C are not the same. So repeats are allowed just kind of in a specific way. So just something to keep in mind. Also notice that if you pick 3 letters that are not the same, so there's no repeats, then 3 will always be satisfied, meaning that the number of ways of performing, of doing this will actually be more than the combination of letters with no repeats. Something to think about, but let's see if we can discuss this. So for each of these, there are different tasks that we'll be doing, and basically they have to do with picking one letter at a time. So we're going to be doing that in order. So we're going to be picking letter 1 first, letter 2 first, letter 3 first. So these are our tasks, picking these letters. We'll pick 3 of them, and it's from A through H. By the way, notice A through H, if you count, there's actually a total of 8 letters. So we have 8 letters to play with, and we want to make, a combination of 3 of these. So the way I like to do this, honestly, is what is known as the slot method. So there's going to be 1 slot for each letter. And in this slot, I'm going to basically just write the number of ways we can perform that task. So the number of ways we can select that letter. So, and then we'll multiply them. So let's see. And you have to kind of think about this a little bit. But let's say we have letters A through H, and we pick one for the first letter. If we pick a letter for the first letter in our code, well, first off, how many choices do we have? We have all 8 of them. So there are 8 numbers that the first number can be, 8 letters that the first number can be. Now once that letter has been selected, let's say we choose B, then we can't choose B for the second one because no repeats are allowed. Meaning we have one less letter to choose no matter which letter we chose, even if we chose a different letter besides B. So we actually have 7 here. Similarly for the next letter, now we have even one less to choose from. In fact, since we already chose 2 for the first 2, we'll have 2 less for the last one, leaving us with 6. So here, 8 times 7 times 6 will be the answer. And let me just do this real quick in my head. So 7 times 6 is 42. 40 times 8 is 320. 2 times 8 is 16, so 320 plus 16 is 336. So that's our answer here. And by the way, this slot method is literally just this principle. So it can get a little tricky sometimes, but just kind of keep that in mind. This, I think, helps a lot. So let's see if we can try that method for the next one. So here repeats are allowed. So let's see, we still have 3 letters to choose from. Well, 3 letters that we're going to select basically of the 8. And let's say we pick one letter of the 8. That means we have 8 choices. And for the second letter, well, we actually still have 8, don't we? Because we could pick the same one again, actually. So there's 8 choices here, similarly 8 choices here. So there are 8 ways we can select the first letter, 8 ways we can select the second, and 8 ways we can select the third. So these are just a number of ways of, again, performing this task of selecting a letter. So we end up with 8 times 8 times 8, which is 512. Perfect. And great. So now, this one is kind of tricky. So let's see. Again, we're going to try the same slot method. Now, we have 8 letters to choose from for the first letter we select. But now, for the second letter we select, it can't be this one, right? So whatever letter we select, the fact that this will be adjacent to the next letter for the second letter, well, that means we only have 7 choices for this second letter we choose, okay? Now, what about the third letter? Well, the third letter, this is kind of funny because even though it can't be equal to this one that we've chosen, it could be equal to the one we chose for this one. So basically the fact that no adjacent letter can be the same doesn't really mean that the amount of options we have decreases each time. It's kind of going to be the same each time after the first one. So for the first letter, we have 8 options. So choose that. Now we'll have 7 for the next one because we can't choose the one we just chose. But for the next one in place here, this one is gone now, so we'll have 6 choices, but this one comes back because now this letter is not the same as this one and it won't be adjacent. Adjacent just means next to. So in fact, we'll actually also have 7 choices for the last letter, which I know sounds a little weird, but you can try to write this out and write out all of the you can try to write them if you want, but obviously there are going to be a lot of options here. But once you start to try to perform these tasks that I'm describing, you kind of see what I mean. Hopefully the principle will be a little more reinforced as far as that goes. But now let's just get to it and multiply these. So I'm going to do it in this order. So 7 times 7 is 49. 49 is 1 less than 50. 50 times 8 is, well, 5 times 8 is 40, so that's going to be 400. But since it's 1 less than 50, it's going to be 1 less 8 than 400, which is actually 392. All right, so this basically does it for 7.3. Again, I only did one example of each principle, but they were kind of on the advanced side of things. So I think that'll be okay in the sense that if you were to try any other examples involving these principles, they'll kind of be more simpler. But yeah, like I said, that's it for 7.3. I'll see you in the next video for 7.4. Thanks for watching. See you then.